Okay, so now we're going to change gears a little bit and we're going to compute volume of a solid of revolution where we rotate about a vertical axis, not a horizontal axis. So I'm not going to draw a picture, I'm just going to write down the formula. Okay, so what we have to think now is we have to sort of tilt our head sideways, okay, and think of what function. So we have to think of x as a function of y, f of y, and another x as a function of y. I call that g of y. And I'll draw a picture in the specific example that we're going to look at. So consider, so in this first example, consider y equals x squared and y equals 2x in the region bounded by those two curves. And we're going to rotate about the y-axis. Okay, so to draw a picture, so the plot of x squared, I'm only going to draw it in the first quadrant, the region that these two curves bound is in the first quadrant. So here's x squared, and here is 2x. So here's y equals 2x, here's y equals x squared. So I'll shade the region. And if we're going to rotate now about the y-axis, if I construct a representative rectangle, hard to see, it has a width of delta y. We have to determine an inner radius and an outer radius. And so this distance here is an inner radius, and this distance here is an outer radius. Okay. So now, what are these functions, and what are these radii? We have to be really careful because we have to get x as a function of y. Okay, and so if we do tilt our head so that we look at this, thinking about which is the outer radius, which is the inner radius in regard to the curves. So the inner radius is easier to deal with, r sub I. The inner radius is related to the graph of y equals 2x. But since we want x as a function of y, the inner radius is actually y over 2. So if we take y equals 2x, solve for x in terms of y, it's 1/2 y, or y over 2. The outer radius. All right, so we want x as a function of y, and in this case we have to be careful. We have to make sure that we're going to take a square root, but we have positive and negative square root. But in this case, the positive square root is the one that we want. So we have the square root of y as the outer radius. So with these two radii determined, now we can use our formula and construct this integral. So the volume in this case is pi. Let's see, I guess let me back up a little bit. We have to determine points of intersection. Okay, so points of intersection. We determine the points of intersection by, here we can just set 2x equal to x squared, and we can see here pretty clearly that the points of intersection are x equals 0, they certainly intersect at the origin, and they also intersect at x equals 2. Okay, but here we have to be careful. Our limits of integration now, so let's go back up to the curve here and to the picture. The other point of intersection has an x component of 2, has a y component of 4. So what do we use for our integral? Well, remember we are integrating with respect to y, and we want values of y, the range of y here. So our volume is equal to pi times an integral from 0 to 4. And an outer radius squared, so our outer radius squared is square root of y squared, or y, and I guess let's do this in two steps. So we have the square root of y squared, and then minus y over 2 quantity squared dy. This equals pi times the integral from 0 to 4 y minus 1/4 y squared dy. And so this turns out to be 8/3 pi. As a variation on this problem, consider rotating about x equals 3. So now our picture we have our straight line, we have our parabola, we have the region, we have x equals 3, which is roughly here. This is the line x equals 3. This is our x-axis, this is the y-axis. And now, when we take a representative rectangle, our inner radius is this distance here, and our outer radius is this distance here. So let's think about what the inner radius is. And now we have to think in terms of x in terms of y. So we know that y equals x squared is the same as x equals square root of y. So let's so if we look at the inner radius, it looks like the inner radius is a difference between 3 and the curve that represents y equals x squared. But in terms, if we get x in terms of y, looks like our inner radius is equal to 3 minus square root of y. So hopefully you can see that this r sub I is the difference. It's the distance between 3, the curve x equals 3, and the curve x equals square root of y. So it's a difference. So it's 3 minus square root of y. Okay. Now for r sub O, this equals, it's a difference of curves, the curve x equals 3 and the curve x equals half of y. So the outer radius is 3 minus half of y. Okay. And so now to set up the integral, v is, so we will have pi times an integral from 0 to 4, outer radius, which we computed as 3 minus a half of y, we square that, and then minus the inner radius, which we computed to be 3 minus square root of y, and we square that, and we integrate with respect to y. This is a setup of the integral, and I will leave the computation of this volume up to you.